It has been a long time.
Very long time.
So Dick, when did you first come into this building?
Well, I came in early April of 1961. The primary tank was open and we were in the process of aligning all of the fuel handling equipment. And we had a requirement of aligning to within a 64th of an inch, 26 feet below. Somehow that happened. I'm Dick Lindsay. I came to the lab in 1961. I was in operations. I was trained on EBR-I for the startups at EBR-II.
So you were actually in the tank?
Yes.
So you walked
Many
around
times.
in the tank before it was filled with sodium?
That's right. In fact, when we put the fuel in for dry critical, we handled those fuel assemblies by hand to load the core. The culture here was just an amazing thing. Maybe it's because of the spin-off from the University of Chicago. Perhaps it had to do with being associated with some of the pioneers, early pioneers in the nuclear business. But the attitude that the designers brought with them, it was a can-do attitude, and it stayed that way for all the years that I worked here.
My name is John Sackett. I joined EBR-II in 1970, and I spent 34 years here. You know, one of the things that was really interesting to me about how things were done here and also at EBR-I was you had this eminent team from Illinois, University of Chicago, folks that had built the very first reactors. As a senior in high school, I said, that's what I want to do, that's where I want to work.
You did.
And I went on to college, got a PhD. 9 years later, I'm back here working.
And you ended up heading up the whole thing.
Eventually, yes.
Hey, my name's Daryl Fonestella. I started at EBR-II reactor operations as a nuclear power plant operator and qualified as a senior operator, then foreman and shift supervisor. I started in 1977, and this place had about a 5-year life expectancy at that time. Obviously, we're still here, and the reactor operated until 1994, so it was a true research reactor. I mean, ideas came up, and we actually put them to use and tested them, and that's what it was just an interesting place to work. You enjoyed coming to work and did different things all the time.
The significance of EBR-II to the nuclear science community was proof that reactors were safe. And that proof came with tests that demonstrated self-protection, the reactor protecting itself, to the worst accidents that could befall a nuclear power system. That worst accident is complete loss of electric power to everything, backup as well, and failure of all of the safety systems to shut the reactor down. We did that at EBR-II, and the reactor protected itself. It shut itself down safely.
I do remember the day that we shut down the coolant pumps, and I was fortunate enough to be the foreman on shift that day. I do recall one person asked me if I was nervous, and it wasn't nerves, it was excitement. We had almost 70 people, and they were there to see this happen. I stood right over there, a few feet from this console, on the phone and directed the shutoff of the primary pumps. The test went just as expected, and as we talked about previously, we got to watch the forces of nature shut the reactor down. That bothered us as operators. Our job was in jeopardy. They didn't need us anymore. We found a reactor that could protect itself.
The day of the final test was one of the most exciting days of my time, to see all of these colleagues, respected scientists from around the world, come to watch this event in a live reactor. I would add that a month later, the Chernobyl accident occurred.
When we ran that test, we had scientific interest, a lot of it. Suddenly, after Chernobyl, we had the major newspapers of the world calling and wanting information. We were written up in the New York Times, the London Times, many of the news magazines and so forth, and it really opened the door. They knew that something very important had taken place here, and it had been done very well.
The basic difference between EBR-II and Chernobyl is that the Chernobyl accident could absolutely not happen at an EBR-II reactor. And that was proven in these tests.
Probably one thing I'd like to say is I enjoyed the fuel handling the most, but selfishly, I sort of really enjoyed it when we had problems with the fuel handling sequences because the troubleshooting was such a challenge. I believe we had a sub-assembly get away and end up in the catch basin, which it was assigned to catch.
In the catch basin and did what it was supposed to do.
You were able to retrieve that one as planned.
Yes.
The second one was somewhat more unique. We ended up having a sub-assembly come off the transfer arm and lay across the top of the reactor grid and angled up on the reactor vessel.
Yeah, and that means that if we couldn't get that out of there, we were through.
We mocked up the reactor vessel and the top of the grid out of plywood, and then we were able to profile where that sub-assembly was using our main core gripper and our transfer arm to feel it. And we were able to get an accurate profile of where that sub-assembly was. And then one of our technicians practiced on that mock-up using a stainless steel snake snare, if you would. With a tube and a stainless steel cable. His second attempt, though, he got that.
He got that, and just a snare, basically at the end of a long tube.
It was exciting to do, and yet, I mean, when you found the problem, and we had a lot of them, but we found them, and the operators were involved in that. You didn't just call maintenance in and sit back and watch them. Everybody got involved in it until you found the problem and got it corrected, and that's what made this a fun place to work at.
Each one of the failures, as I see it, taught us a lot.
Working with sodium is not something most people are used to, and so the question often comes up, is it difficult? You know, isn't this dangerous? Because everyone has seen the sodium chemistry demonstration where you drop a bit of sodium in and it sputters and flames. And
sodium is a liquid metal. The way we use it in the reactor as a coolant, we kept it liquid. It's very good heat transfer capability. It doesn't boil until 1618 degrees Fahrenheit. That means that when you're operating with temperatures in the reactor that are below that, there's no way you can pressurize the system.
The physics are such that the sodium does not capture and slow down the neutrons that contribute to fission. So you have a very efficient process, and that's what allows you to breed more fuel than you consume. Most of our operators had experience from the nuclear Navy, had experience with working with water-cooled reactor systems, but everyone, after having time with sodium, said that they would all prefer working with sodium than in pressurized water systems. Is that true in your experience, Daryl?
I did have experience for about 6 years on pressurized water reactors that operated anywhere from 1,600 to 2,000 pounds. They had leaks. Leaks in those are scary. That's how we explain the difference between a major and a minor leak. You find the minor ones, the major ones find you. But after a few years working with the sodium reactor, it was very easy to work with. You gain a healthy respect for it. When sodium is solid, it's much the consistency of peanut butter, and it's not near as reactive when it's solid and exposed to air. You could cut these pipes out, clean them up, and change components, actually put them back in the system and weld on those. So we had a lot of experience with that. And after you experience that, you find out that this stuff is manageable. You just have to know how to treat it.
Another interesting thing about sodium that most people didn't appreciate, and I'm not sure we did early on, sodium did not react with our structural stainless steel. And after about 20 years, you remember we took a superheater out and sectioned it up and looked in there, and you could still see the marks that the millwrights made on the tubes. The sodium had not eroded nor corroded anything. It looked like brand new when it was cleaned up.
That was a very huge advantage of sodium, is there's absolutely no corrosion, and we didn't really know that until we did drain the system.
In every way then, it was the ideal coolant for reactor systems.
If I ever see another pressurized water reactor again, it would not bother me. This is the technology to go with. Yeah.
There was a vision about EBR-II that had to do with secure energy, safe energy, clean energy. And when you get your mind around some of the things that drove the vision of the people who started this, it is really compelling. The integral fast reactor was a combination and integration of all of the things we had learned from the EBR-II and the fuel cycle facility experience. It integrated all of the best of the technology that we had developed and discovered, not only here, but worldwide.
The thing that we were promoting was you take a complex like EBR-II and you build 8 of them, as an example, and put a fuel cycle facility in the center of them. The concept was to haul enough fresh uranium on site at the beginning of life to supply all of those plants through their whole lifetime, 40 to 50 years. With a breeder reactor, you could even go one step farther in that you could produce more fissionable or fissile material than you were consuming, so you had an infinite supply.
This facility is one that virtually gives the Earth and its inhabitants an unlimited power supply.
What it was a culmination of 4 distinct periods of testing in EBR-II's history. One was its initial operation as a complete power plant, producing electricity, recycling fuel. The second phase was irradiation testing of fast reactor fuels, and we tested metal, we tested oxide, we tested carbide, we tested nitride. So we understood fuel behavior across the spectrum. The third phase was what we called operational safety testing. And in that phase, EBR-II pushed the envelope, and we developed the testing program that led to the demonstration of self-protection of the reactor to loss of flow without scram and loss of heat sink without scram. The fourth phase then put all of those things together to incorporate this advanced fuel reprocessing and recycle technology. We recycled 700 subassemblies of fuel back to the reactor in the course of 4 years. And a big part of that was what's in vogue now, and that is burning nuclear waste, which means taking those elements beyond plutonium and showing that they could be effectively incorporated in fuel and destroyed.
Because we were burning the transuranics, as you mentioned, that then would make our waste repository, you still need them, but it changes from a mega 1,000-year problem to 1,000 years, maybe at the most. And we have buildings much older than that. Economics is something we'd love to have operated long enough to get a better handle on, but EBR-II in many ways was a cheap date. When you look at the money that's poured into research today, EBR-II was very economical.
Used in a system like this, we have enough uranium already mined and set aside to supply the energy needs of the United States for several centuries. Well, very good, guys. It's hard to imagine this is one of the last days that anyone will be able to see this structure as we see it now. But a great run starting in 1961. In all of that time, there have been no serious injuries. It's a major accomplishment.
When we first heard that we were going to be shut down and decommissioned, initially I didn't believe it. We heard rumors a lot of times. I actually didn't do much with the reactor other than maintain it shut down, hoping that it would change.
When I had to go to the operating crews and tell them that we had gotten the order to shut EBR-II down, the reaction was not what is going to happen to me. The reaction among all the crews was, doesn't the country realize what they're losing here?
The one thing that was hard for us to do, we don't mind something being taken out of commission if it's broken, but this was a neat machine. Wasn't anything wrong with it, but we had to shut down. So
it's sad to see such a success be decommissioned. You knew full well that decommissioning a facility like this had to be shown.
Right.
And nobody else had shown things any better than we had, so why not us do it?
There was a sense of mission extraordinaire that captured the original vision of the pioneers who started this whole thing with EBR-I. And that kind of vision carried through here until the end.
And another thing after we shut down, we had to account for all the nuclear material that went in that tank, and it had to be exactly where we said it was. But when we pulled it out after we shut down in 1994, every subassembly was exactly where we expected it to be, in the exact orientation we expected it to be.
And the debate about shutting EBR-II down had gone on for about 3 years. And the debate in the Senate initially started out as a debate over budgets, and the Japanese stepped up and said, we're willing to add another $60 million to the budgets at EBR-II. So they took away the budget argument, and then it became an argument about the political nature. If the United States terminates its work in nuclear power, the rest of the world might follow. But it was decided by full Senate vote that the program would be terminated, and DOE was directed to terminate the program and shut EBR-II down.
But we finally did get the shutdown order in September. Matter of fact, again, I don't know why I was so lucky. I was a shift supervisor on duty the day that we started up to shut down for the last time. That was September 30th, 1994. So it was a Black Friday, if you would, because it was a Friday. Had quite a crowd in the control room.
But it was, I really can't talk about the day that we actually shut down. The guys that gathered here in the control room, they tied me in by the phone so I could hear. I remember the reactor shut down and then the scramble into silence.
Are we proud of what we did? I certainly am. And thinking back on it, I have no idea what I would have done differently or better. But nevertheless, that was a sad day to see the grand old lady put to bed, as it were, and realize that maybe in my lifetime I would not see a resurgence to drive the technology as far as we had taken it. Don't forget what EBR-II did. The technology is there. Let's move on and build something new.